Okay, so we finished all the material, and for today I'm not going to do too much actually. You can prepare for your quiz and perhaps also start thinking about the quizzes next week, the big quizzes next week, right? So will be, so yeah, perhaps this might be a place that I could say this. I'll also post it on my website. So on next week, Tuesday, no, let me don't do this in this movie, otherwise it gets too much. Okay, I'll post it elsewhere. But so remember, we're going to have big quizzes later. Okay, so the review of subspaces and eigenspaces. I just want to quickly go over the things that we have done basically in these few chapters. So first of all, we have seen we talked about what a vector space is, and we basically the only examples that we looked at were the n tuples vectors of size n, where most commonly we work with r square or r cube, right? The things that we recognize, two-dimensional, three-dimensional vectors, but it is possible to work with higher arity vectors. And so then we had the notion of a subspace, and it was a collection of vectors that was closed under linear combinations. That's really what a subspace is. Meaning, if you take two vectors in there and you make an arbitrary linear combination of these two vectors, that should be again in there. And then we noticed that these subspaces are some things that we are familiar with. If, for instance, in R cube, there are two silly subspaces. There is a zero subspace, which consists only of the zero vector. So let's write it like that. There is the subspace that consists of everything, because obviously if you take a linear combination of two things in R cube, you get something again in R cube, right? So these are the silly ones. But then the interesting ones are the lines through the origin, and also the planes through the origin. Now, it has to be through the origin, otherwise this linear combination thing doesn't work. I gave examples there. So, and then what the next step we did was that if you have a vector space, we know with a vector space you can find a basis. And the basis was it was a collection of vectors, finite number of vectors, that was linearly independent. That meant that there was no relationship between them, really. That's really what it means. And formally, this meant that if you take a linear combination of these basis vectors and you put that equal to 0, then there is only one solution, namely just 0 everywhere. And that even then spreads out, not just, let me say it that way. And it is also generating, meaning that every other vector can be written as a linear combination of the basis vector. And so a basis is a basis means that every vector is a unique representation or can uniquely be written as a linear combination of these basis vectors. That's what a basis is, that every vector can be written in a unique way as a linear combination. And then the coefficients of this linear combination, so the coefficients that we called in this linear combination, that's what we call the coordinates of a vector. So bases were very interesting to study vector spaces, but subspaces are themselves vector spaces. So what we actually really do is not find a basis for the whole space, but basis for these subspaces. Okay, and so what we noticed, then we could see a bit of a difference here between these guys here. Well, okay, R cube, we know that, for instance, we have the standard basis here. The standard basis is the basis consisting of the vectors, I'm going to write this as columns, 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's what we call the standard basis. Notice that there are three of them that corresponds to this tree, and we call this we actually didn't discuss it really formally, but let's say it now. The dimension of the space, of the vector space, is by definition the number, the size of its basis. Okay, so here we have 3 basis vectors, the size is 3. Now, what's a line? We know a line was given by a single vector here that and all the multiples of that vector, and that single vector would then be a basis. So this would have dimension 1. But lines are one-dimensional, right? And what about in a plane? Well, in a plane we would have in 3 dimensions. Of course, this is of course all in 3 dimensions, right? But so in 3 dimensions we would have I cannot draw. I'm not going to draw this. I'm very bad at drawing. So, but in a plane you would have 2 vectors, right? Say this vector and perhaps this vector. Let me get rid of these tails here. So these 2 vectors then would span a plane. Okay, and so here the dimension would therefore be 2. Okay, now that's basically the theory. And then how did we get subspaces? Well, we talked about if you have a matrix, then we can talk about the column space and the row space of this matrix, and also the null space. So there were 3 different spaces, subspaces that we associated to a matrix. So let me give an example here. So for instance, let's look at this matrix here, 1, 2, 0, 2. We might have done this better. I'll do it again. -5, 5, 6, 0, -3, 15, 18, 0, -2, 10, 8, and 3, 6, 0, 6. Okay. So what is the column space? Well, that is the vector space spanned by these 4 columns. Okay. So this is now, in this particular case, a subspace. Well, each of these columns is a vector of size 5. So these are subspace of R5. Okay. But the row space is the subspace spanned by the rows. And so these are 4 vectors. So this is in R4. Okay, so the bigger for column space and row space are different things. Now, what is the null space? The null space corresponds to thinking of this matrix as the matrix of a linear system of equations. The null space is just the solution space of that system of equations. So the null space is the solution space. So we have here vectors variables x1, x2, x3, x4. And so this will be a space in which these values, these vectors x1, x3, x4 can have different values, and so this will be a subspace of R4, right? Because there are 4 variables, they will have, every solution will be a 4 vector. Okay, and this is of course because our matrix here, what is our matrix? It's a 5 by 4 matrix that we had. Okay, so it's a bit perhaps, I don't know how you want to memorize this. It's sometimes easier to just look at an example, right? So there are 5 rows. That means that every column is a 5 vector. So that's why the column space is in R5. There are 4 columns. That means that every row is a 4 vector. That's why the row space is 4. And if it's a 5 by 4, if you think of it as equations, means there are 5 equations in 4 variables, therefore the null space is in R4. Okay, so let's look at how we calculate all these things. Well, and this is, of course, you see actually, in some sense, there's only really one question is, each time is row reduce, row reduce, row reduce, row reduce your matrix. Okay, so let's see how this works here very quickly. We have a pivot here, so we're going to do row 2 plus 2 times row 1, and only this one I have to take care of, that's row 5. Don't see that often, right? Row 5 minus 3 times row 1. So we get 1, 2, 0, 2. Now, so we multiply this with 2 and add up there, so that's 0. 4 minus 5, -1. 0 plus 5, 4 plus 6. Then we just copy these guys. By the way, I actually noticed that I could divide, so I'm going to do this here because it just saves me one more writing. There's a lot of writing here. Why can I can do something with these the third and the fourth row because I'm not doing anything else here. So I could do actually this and divide by minus 1/3. And in fact, I can also do this with row 4. Let's just do this. I divide by 2 here so that we have a little bit less of big numbers. So then here, so I'm dividing by -3. So we get a 1 here, -5 and -6. Then I'm dividing by -2, I get a 1, I get a -5 and a -4. Okay, now we're doing this -3 times and add up there, so that's a 0. -6 plus 6, that's a 0, that's a 0, and then oh, that's a 0. So that we already get 1 0 row. And once we have a 0 row, we can kind of ignore that row. Okay. Yeah, okay. I have a -1 there. I could swap 2 rows, but I'm just going to do row 2 minus row 2. I'll write it out, so otherwise it gets sometimes a bit confusing if you do it on the spot there. So it's 0, 1, -5, -10, 0, 1, -5, -6, and 0, 1, -5, -4. Okay? So the next operation is row 3 minus row 2, and row 4 what am I with my arrows? Well, okay, let me make this a little bit nicer. Minus and yet minus row 2. Okay. So we get 1, 2, 0, 2, 0, 1, -5, -10. So I'm multiplying this with -1 and add this up, so we get 0. 0 there, also 0 there, and then plus 10 minus 6, that is 4. I get 0, 0, 0, and now I get plus 10 minus 4, that is 6. Okay, I can get again rid of these guys by row 3, 1/4 of row 3, and row 4, 1/6 over row 4. I don't need to do the second one, but since I'm at it. I get 1, 2, 0, 2, 0, 1, -5, -10, 0, 0, 0, 1, 0, 0, 0, 1, and I'm not writing the 0 row anymore. And then finally, then to get my echelon form, I do this here, and now I have an echelon form. 1, 2, 0, 2, 0, 1, -5, -10, 0, 0, 0, 1. And this is a 0 now. Okay. This is as far as I need to go for the first two problems, because I have my pivots here. Let's mark the pivots. These are the pivots. So this is, remember, x1, x2, and x4. This means, let me already mark it, and we won't forget this later, that x3 will be the free variable. Okay. So once we have the pivots, that means once we're in echelon form, not reduced, just echelon form, which, by the way, is not unique. Okay, so you might do different row operations and get something else here. Once you get this thing, you can write down what the row space is. Let's do the simplest one. The row space, or the basis for the row space, is now, you just take these 3 rows. It's this guy, and this guy. Okay, since there are rows, I'm going to write it as vectors really. This guy, 0, 1, -5, -10, and 0, 0, 0, 1. Notice that these are not the original rows, right? And it doesn't not necessarily mean that the first 3 rows originally were the right ones, because we have swapped rows around. Are a basis, I mean. So, but this is for sure a basis of a row space. It's the row space and it's the basis for it. Now, the column space, we have to be a little bit more careful, because what happens in the column space is that when you do row operations, you do actually change the space. Row operations don't change the row space, but they do change the column space. However, whatever was linearly independent originally still remains linearly independent, and therefore is the basis. So what we need to do is we look at the 3 pivots, and the pivots tells us what the original columns are bases. So 1, 2, and 4, that means this, and this is a basis for the column space. Sorry, I'm going to now use this here. I'm not going to copy it anymore. Okay, you have to go back to the original matrix. That's why it's different. Okay, notice by the way, this is kind of also because here, because of the 0 rows, I kind of don't write them anymore. It looks like now my columns are 3 vectors, but no, we know that the columns have to be 5 vectors. So that's another perhaps indication or motivation why we need to go to the original matrix. Okay. Now we know that what are the dimensions? We know that the dimensions, they have the same dimension, and this dimension is equal to the number of pivot variables. Remember that, right? This is exactly what we have here, right? The number of pivot variables is exactly the dimension. Okay, so now the null space, therefore the null space, so for the null space, we have to go to the row reduced echelon form. Now, we are not that far away of it. We have these 2 blue pivots. Now we work from the bottom upwards, right? So the first one that we have to work with is here. So we're going to do row 1 minus 2 times row 3, and row 2, row 1 plus 10 times row 3. So it's the row 3 that I'm working with. That's why I'm adding certain multiples of that row. Okay, so we get, so what I'm doing, okay, that's 1, 2, 0, and then now negative 2 times that is 0, and then this one is 0, 1, negative 5, 0, and then 0, 0, 0, 1. Good. Now the only thing is this one, the 2 above it has to be gone, so we have to do one more row operation. So that is row 1 minus 2 times row 2. So I'm going to do this minus 2 and add up, right? So I get a 1, 0, 10, 0, 0, 1, negative 5, 0, 0, 0, 0, 1. So again, remember we have these 3 pivots. We already analyzed this, but let me do it again. And the free variable is x3. So to write down the null space, we have done this now many times. You write down the pivot variables, the blue ones, in terms of the green variable. Okay, so, and we get these equations tells us exactly how. The first equation tells us how the first pivot variable is written. The second equation, the second pivot. It all matches all together. So x1 is minus 10 times x3. x2 is equal to 5 times x3. Now x3 is always equal to itself. Don't look for an equation here, there's none. And then finally the fourth pivot variable is 0. We factor out an x3 and we find minus 10, 5, 1, 0. And that's the basis. This is the basis for our null space. Now, we also know the dimension of the null space. The dimension of the null space is exactly, so the dimension here is the number of free variables. Okay, the number of pivot variables was the dimension of column space, which is also the dimension of the row space. The dimension of null space is the number of free variables. Okay, and by the way, notice that they add up, right, to 4. 4 being this 4, because we have 4 variables, right? Right? How many variables are there? 4. That's the number. That is this 4. Tells me the number of variables, and well, you're either pivot or either free variables. Okay. So that's the general theory of certain. There are of course other subspaces, and in fact we now so eigenspaces were a very special case also of null spaces. These were null spaces not of the original matrix but of the matrix. So we have a matrix A, and then we would subtract and lambda times the identity matrix. Now, okay, this is for square matrices. Sorry. What I just did was for any matrix, right? So I gave an example of a 5 by 4. I couldn't, of course, it works also for square ones, but it doesn't have to. But when we talk about eigenspaces, then we're talking about square matrices. And so let's say of square n by n matrices. So we take, we look at these kind of matrices which It's a fancy way of just saying I subtract lambda from the diagonal. And we look at these matrices where this is 0. So for which lambda is 0, the determinant is 0. Because what does it mean? For the determinant of... So we noticed that, let me go back very quickly. The null space has dimension equal to the number of free variables. Okay. Now what if there are no free variables? That dimension is 0. What is that 0 dimensional? Well, let's look at our picture with dimension 1, dimension 2. Where does dimension 0 lie? Here, right? This means there is 0 number of basis vectors. It's kind of weird, but yeah, there's only the 0 vector, and the 0 vector is itself. There's nothing to write. There's no linear combination, right? So 0 dimensional means basically just a single, it's just a singleton 0, right? Now, we know that an eigenvalue is exactly when this is not, when the matrix A minus lambda. So what is an eigenvalue? That means that A times a vector V is lambda times a vector V, or that means that A minus lambda En V, this is just writing this equation in on one side, equals 0. This tells me that I have an eigenvector is always a non-zero vector. So to have an eigenvalue means exactly that you have a solution that this matrix, or the system of equations with that matrix, has a non-trivial solution, which means that this has to have a free variable, right? The null space cannot be 0 dimensional. The null space has to be more than 0 dimensional, 1 dimension, 2 dimension perhaps. And that means there has to be a free variable. But in a square matrix, to have a free variable means that your reduced echelon form is not identity, and therefore exactly means that your matrix is not invertible, which exactly means that the determinant of this matrix is 0. And that's why we write this. Okay? So eigenspaces are therefore, again, null spaces, but not of the original matrix, but of the matrix where we subtract the eigenvalues, and they're only finally many, given by the characteristic equation. Of course, what I actually wrote down was the characteristic equation, right? If you write this up, this gives you an equation in lambda of degree n, right? The degree n here, which is not easy to solve, but in principle we can do that. And so yeah. And that's now what do we do then? Right. So that was the theory of eigenspaces. Now the applications of this. So applications were, well, first of all we had diagonalization, and that meant that we could write a matrix A. We could find an invertible matrix P, so that this was a diagonal matrix. And the diagonal matrix is up to the order in which you put the eigenvalues unique. If it exists, but not every matrix was diagonalizable, that we also noticed that. And so let me repeat here this, let me write it also, I said it, but let me write it down, this P is invertible, right? And how do we find this P, if it exists? What we needed to do was to calculate all the eigenspaces, find basis vectors for them, and put them all together in a matrix. Now, if there are not enough of them, you couldn't build the matrix P, right? So, for instance, if n is 4, you needed to have a basis, 4 basis vectors, but it could be that there are less. We have seen examples where there are less. One case where we are sure to have, let's say 4, if n is 4, is that if all the eigenvalues are different. So the problem can only come from eigenvalues that are the same in this equation, so with so-called higher multiplicity. Now, let me not go to the details of this, but that was the how we built P. Now, part of the question also then was to what is P inverse then? So sometimes we had to calculate P inverse, right? I asked you, please calculate P inverse, which was a technique that we had learned before. There are actually 2 techniques. There was either you could use row reduction, or there's the technique where you use the adjoint. Depending a little bit how many zeros are in the matrix, one might be better than the other. Although I'm inclined to always do the row reduction. I find that always easier. Okay, but that's a bit of a nuisance that we had to calculate this inverse. So we had the next application was orthogonal diagonalization, but there we even had to be more restrictive. The matrix had to be symmetric, because otherwise it's not possible. So we needed a symmetric square matrix. And what was then, because in that case we could make P inverse to be P transpose. Okay. And yeah. So, and there was also something that we did not really prove, but it actually turned out that symmetric matrices always are diagonalizable. So the problem that we discussed just before that doesn't happen for symmetric matrices. Now, we didn't do the general case here because we still would have a little bit of a problem of doing when we have an eigenvalue with multiplicity, higher multiplicity than, let's say, multiplicity 2, we would have two basis vectors, but they might not be orthogonal. So we had to do something Gram-Schmidt procedure which we haven't discussed. So we only, when orthogonal diagonalization, we do symmetric matrix with different eigenvalues. So I'm going to put this here, although this is not necessary in the general theory. For us, that is what we do with different eigenvalues. Meaning if this is a 3 by 3, there will have to be 3 different eigenvalues. Okay? So, but the advantage of this was that, okay, it was a bit more work because we had to normalize, but once we had our matrix P, it was very easy to find the inverse of the matrix because it's just a transpose. Transposes are very easy to write down. Okay, so that was the benefit of having orthogonal diagonalization, but it only works for symmetric matrices, and we can only do it if the different eigenvalues are different. Okay, and then the last application was a quadratic forms, what I just gave a review for, and there will be a quiz next time. Okay, on quadratic forms, we do basically orthogonal diagonalization, and then the diagonal matrix tells us exactly what the coefficients of the squares are, and all the rest, there are no cross terms, all the other coefficients are 0. Okay, so that's what we have been doing with subspaces and eigenspaces, and so this is the kind of questions that you can expect. I mean, it's not a review of a test, it's a review of the material that we've done. And I'm not really going to assign homework problems. I want you to catch up with all the homeworks because some of you haven't done this. Go back at the homework. So start preparing yourself for the big quizzes that come. So next session, I'm going to do a review. So yes, the quizzes, just quickly, will split in 2 parts. The part that we covered before the online, before we switch to the distance learning, and after. There are different material that we approach differently, so also I'm gonna do the questions slightly differently also, okay? But I will address this next time in much more, when I do a review of the problems, then I will tell you exactly much more in detail what kind of questions to expect, okay?